Okay, so we are going to go very quickly through some sections 11.1 and 11.2. These are sequences and the introduction to series, which we have talked about in class. And I want to just recap a few of the things that we said in class in this video. So it shouldn't be too long. So to start off with, a sequence is just a list of numbers, an unending list of numbers. A1, A2, A3, A4, forever. We saw examples of these. We usually have a formula. So for example, we have about n over n plus 1. So this sequence looks like a half, 2/3, 3/4, 4/5, and so on. Here's another example of a sequence. How about minus 1 to the n plus 1 times n plus 2 divided by, I don't know, 5 to the n. We saw this one in class. I think this looks like 3 over 5 minus 4 over 25, 5 over 125, minus 6 over 625, and on and on and on. So this is the notion of a sequence. It's a list, right? So an unending list. All right, so we had the notion of the limit of a sequence. We could ask whether or not a sequence has a limit. If this is true, if the limit of these terms approaches some number, then we say the sequence has a limit. So the sequence has limit L, and all that means is that that means the AN are approaching L as n gets very, very big. Okay, so for example, we have, I don't know, how about this? 2n over n plus 1. So what's happening to this as n gets bigger and bigger? Well, this is a ratio of two polynomials in n, and so really it should just be approaching 2 over 1. How we might see that is by pulling a copy of n from both the top and the bottom, so that leaves us with 2 in the top and 1 plus 1 over n in the bottom. Those cancel each other, and then this is going to 2 over 1 plus 0, which is 2. So the limit of this sequence is L. Or I'm sorry, is 2. Another example that we saw, if we took an to be 1 over n raised to the p power, where p is any positive number whatsoever, this sequence has limit 0, because the denominator gets larger and larger and larger. Another example, we had the sequence an equals minus 1 to the n. So this bounces back and forth, okay? That is between plus and minus 1, so it looks like minus 1, 1, minus 1, 1, and so on. Here the limit does not exist. So the limit of these an's does not exist. Okay. Curious whether or not you can see that. You can. Okay, good. So that's the notion of the limit of a sequence. We had a couple of laws. So that was if an goes to a, so the limit of the an's is a, and if bn's go to b, then we can take an and we can add or subtract bn from it. This limit will just be the sum or the difference of the limits, depending on what sign you choose here. That's the sign that you get there. So there's one law. If we have an times bn, then this goes to the product. If we have an over bn, then this goes to a over b, as long as b is not 0. Okay. Then we also have if c is a constant. So if c is a constant, then the limit of c times an goes to c times a. And finally, if f of x is continuous, is a continuous function, and if a sequence takes the limit L, then the sequence f of an approaches f of L. Okay, so an example of this might be the example of this last one. Suppose we went to that, we had our previous example, an is 2n over n plus 1, and then we might ask ourselves, well, what about this? So the limit of e raised to the 2n over n plus 1. Okay, so e to that power as n goes to infinity. So the limit of the an's is 2, so this limit is just e to the limit of the an's, which is e squared. Okay, so that's the notion of, or well, some laws related to sequences. Great. We saw a theorem that we had. So this was a theorem. If the absolute values of the terms of a sequence go to 0, then the sequence itself goes to 0. Okay. The prime example of this would be something like that. So if you had an equals minus 1 to the n over n. So what does this sequence look like? It looks like minus 1, 1/2, minus a third, 1/4, minus a fifth, and so on. This is the list. Okay. The absolute value of an, in this case, is 1 over n, and 1 over n goes to 0. Therefore, the sequence a over n also goes to 0. So this is applying this theorem right here. And we saw one other example that we worked on extensively in class. So this is when an was equal to r raised to the nth power. Okay. And we asked ourselves, so r is just some number. So r is allowed to be any real number. So that's what this means. R is a real number. So we look at the limit as n goes to infinity of r raised to the nth power. What we computed in class was that this was equal to infinity if r was bigger than 1. Well, it's 1 if r is equal to 1. It's 0 if r is less than 1 in absolute value, and it does not exist if r is less than or equal to minus 1. So these were the results for our sequences section. Okay, moving on to series. So you guys will recall that a series, we had the following motivation. Okay, this motivation was very important, I thought, in class, and that was we looked at this polynomial, which was the the polynomial from 1 to infinity of x to the 2n minus 1 power times minus 1 raised to the n plus 1 over 2n minus 1, this quantity factorial. This thing looked like this, if you guys will recall. This is messy, but this is what it looks like. It looks like x over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus, and then we just keep adding terms that look like this with odd numbers. And we saw that this thing behaves exactly like sine of x. Okay, and there's a sense in which if you allow this sum to go to infinity, it does behave. It is sine of x. If you put any number in for sine of x here, put the same number in for x in this, and you analyze what that expression tends to, it tends to the value of sine of x. So this was just our motivation. We'll see why this is true later in the course. But now let's go back to the definition. So a series is just an infinite sum. So we usually will start, maybe we'll start from 1 here. We have you have just a sum of an infinite number of terms. So these are called the terms. Okay. We had the notion of a partial sum. So Sk is called the kth partial sum. Partial sum means you just sum up to k. So n starts at 1, you stop at k. So we get a1 plus a2 plus a3 plus up to plus ak. And we stop. We don't go any further than that. This is the kth partial sum. And we had a definition if the limit of the partial sums, so if Sk limits to some number, then the series converges to that number. So we call it S, then the series converges to S, and S is the sum. That's our language. S is the sum. So we had, so this is our language. If it doesn't, then it diverges. We say it diverges otherwise. Otherwise, diverges. This is if the partial sums don't have a limit. Great. So let's see, we saw our principal example here was geometric series. Okay, so these are geometric series. These are series of the form a plus ar plus ar squared plus ar cubed. On and on and on, they look like this. Here we're not going to start at 1 anymore, we're going to start at 0. It doesn't matter where you start. So we do a times r to the n power. So that's what this series looks like. And our main result, okay, so this required a proof for super bonus points. So I'll leave that up to you guys to learn and remember from class. But our main result here is that the sum here is equal to the following. It's equal to a over 1 minus r as long as r is less than 1 in absolute value and it diverges otherwise. So if the absolute value of the geometric ratio is less than 1, then this series has a limit. If not, then it diverges. So I guess we had some examples about this, but we did tons of examples in class, so we'll just leave it at that. Okay, that is review at this point.